So welcome to the revision video for IGCSE Physics. This is just one whole topic. There are some more videos which are individual subsections, but this is for if you finish the entire topic. So there are 8 videos in the series. If you like and enjoy, please subscribe. Okay, so it's IGCSE Physics, little introduction to section 3B, wave properties. So we've got a lot of little terms here. So we've got degrees, so how we measure an angle, 360 degrees in a circle, same as 2 pi radians. Use that to measure angles from the normal from a surface to explain wave behaviors. So like when we're doing the law of reflection, you've got to measure it from there. So angle of incidence and the angle of reflection from there off a plane surface. So that's another part of the unit. We need to know about wavelength, symbol lambda, Greek letter, distance from a point on one wave is equivalent to a point on an adjacent wave, and wavelength is measured in meters normally. Could be kilometers, centimeters, but you have to convert to meters if you're using the wave equation. Amplitude of the wave, that is its maximum point. So if we look on this one, so from the middle of the wave here, it's how much it's going up by or how much it's going down. So it could be plus or minus A. Higher it is, the more energy it has. Now, frequency can be tricky. It's a number of complete waves passing a point in a second. So how many arrive per second? So, of course, it's measured in hertz. A frequency of 5 hertz means there must be 5 complete waves passing a point in 1 second. Frequencies are given in often kilohertz or megahertz, and you've got some conversions to show you what it is. So, like, very straightforward. Time period is to complete 1 wavelength. So the time period is actually weird. It's the reciprocal or inverse of frequency. So if I know how many hertz it is, I do 1 over that and I get the time period. Frequency is the opposite. Frequency is 1 over the time period. So if it took a whole second for a wave to arrive, 1 over 1 is 1, frequency of 1 hertz. And then the last formula is the wave speed. Wave equation is frequency times wavelength, which is V is F lambda. Now for a normal mechanical wave, we use V. If it's an electromagnetic wave, we use C, which is the speed of light in a vacuum. Now then, a couple of other things. So we've got transverse. So the wave might be traveling from left to right. The vibration of the particles, or it could be the electromagnetic wave is also transverse, is from side to side at right angles or 90 degrees to the direction of travel and energy propagation. Longitudinal, a slinky can show it quite well by actually the springs coming closer together and further apart. So we get compression and rarefaction. One compression to the next compression is equivalent to the wavelength in this case. You can see here the wavelength. So particles are moving parallel to the direction of the wave travel. Refraction, so waves will slow down or bend towards the normal as they enter a prism like this. So there's glass and here's air, and the wavelength becomes shorter. So velocity slows down, frequency is a constant, so no color change, but the wavelength will go down as well. So wavelength is proportional to V. Waves will speed up when they exit the less dense medium and they will bend away from the normal, which you can see here. And you've got incident and refracted angles, and then refracted and incident angles. Again, effectively, I've put the R there, it's the R one, but they are the same. That one at the top is the same as that one at the bottom, and that one here is the same as this one here. And you also might get a weakly reflected ray as well, because it will obey the law of reflection. So that's your basic wave properties. Okay, so this is an introduction to wave properties. We're looking specifically at the EM spectrum, section 3C on the IGCSE Physics. Okay, so what we're looking at, so we need to know about wavelength, so the distance from a point on one wave to the equivalent point on an adjacent wave. That would be lambda, wavelength measured in meters. The amplitude, again, we still need to know about that, and it's the maximum disturbance of a point on a wave away from its undisturbed position. The higher it is, the more energy it has. We need to know about frequency, so the number of waves passing a point in 1 second. That's measured in hertz. It might have a prefix, a kilohertz, a megahertz. 1,000 hertz is a kilohertz, and 1,000 kilohertz is a megahertz. We need to know about some ideas of dangers. So microwaves cause heating of body tissue, infrared burns your skin, ultraviolet damages the cell surface and can cause blindness, or also you can have some cancer. Gamma rays, mainly cancer mutation, describe simple protective measured against the risk, that kind of thing. We've got some maths in here. So all the EM waves travel at the speed of light in a vacuum, so the velocity V is 3 times 10 to the 8 meters per second. So we use the same wave equation, but we put a C instead of a V.
Note that if something is going through a medium, so it could be a brick wall, it will slow down a little bit, but it's a tiny amount. So it's still traveling very fast, much faster than sound. Uses then radio, microwaves for cooking and satellite, infrared, heaters, and night vision, visible, will be optical fibers, photography, ultraviolet. You might have fluorescent lamps to detect forged banknotes. X-rays will look at the structure of materials or medical applications, and gamma is sterilizing food and medical equipment. Now, the concept really of the M spectrum with all of this is that we have an increasing wavelength, which means then we have a decreasing energy going, increasing energy going across to the left. So if your wavelength is longer, you don't deliver as much energy because your frequency is lower. Whereas if you've got a gamma ray with a very short wavelength, it's harmful. So harmful on the left, gamma, X-ray, UV. Infrared, microwaves, radio are less harmful. And sandwiched in the middle is the visible spectrum. Roy G. Biv. It's a really easy way to remember it. Red, orange, yellow, green, blue, indigo, violet. Now, a key concept to think about all of these properties is, depending on what type of waves you are, means that you interact differently. So different parts of the spectrum, so like radio or micro, behave differently depending on whether they're transmitted, reflected, or absorbed by matter. So there's lots of little diagrams like this where you have to think about how certain waves are reflected, absorbed, or scattered by, say, the atmosphere. And this can happen for any of them, really. So it's getting a bit of a handle. If you want to do well on the topic, you need to know all the ins and outs of that. Okay, so this is an IGCSE introduction into light waves. It's topic 3D. So we've got key maths in this topic of all the electromagnetic waves travel at the speed of light. So light will be 3 times 10 to the 8 in its velocity in a vacuum. It will slow down though in a medium. So although we use C equals F lambda, we've got something called the refractive index of a substance found for the ratio of the sines of the angles of incidence, angle of refraction. If you want to look into it, please do. But at GCSE, we just do the formula. A level will look at the derivation, which is dead clever math. So N, this number, refractive index, is sine I over sine R. So if I have on this diagram here, I've got I and R. I do it on my calculator in degrees, and I get a number. This number typically for a prism would be 1.5. For a diamond, it would be like 2.4. So it's a number greater than 1, but usually it would be less than about 2.5. So you know if you've gone wrong in the exam. You also know if you get the angles upside down, you'll get like 0.7 or something instead of 1.5. You must get your angles the right way around, otherwise it doesn't work. Now there's something else, a formula for the critical angle, which is sine critical angle is 1 over n. We've got this really strange situation where if you look at my pictures at the bottom, we've got an incident ray coming in at an angle, and when we're less than something called the critical angle, the ray will be refracted out the back. But as I increase the critical angle, the angle to the critical angle, or I gets bigger, you can see how the angle's moved across, it's got wider. The refracted ray will graze along the edge of the boundary between the prism and the air. That is when the formula, this one, simplifies to this. So if I know what the critical angle is, I can work out n for the prism. If you go above that angle, greater than the critical angle here, then we're going to reflect the ray back outside on this side, and we call that total internal reflection. Now, total internal reflection is a concept used in optical fibers called TIR, and we can pass light down a fiber, and it will take information cheaply on scale, and it's used quite a lot nowadays. Refractive index and color, we should know that visible light will all split into a spectrum, and it will be dispersed effectively because each of the different wavelengths interacts differently with the medium. So violet will always be refracted more, so you'll get an angular spread. Still need to do the law of reflection, which we looked at before. And like we said, we've got to be able to measure refractive index. We've got to be able to do methods that give a pair of angles, so like this one, and a pair of angles here, to work out the refractive index of a prism. You've got to be able to write a lengthy practical to do it. So there we go, 3D light waves introduced. Okay, so we're doing IGCSE little intro topics. It's 3D part B, second part of, so it's sound waves. So we're already looking at light. So sound waves, you need to know about hearing ranges. So you need to know actually that for human hearing, it's 20 hertz to 20,000. You might not be able to hear that much, maybe as an adult, 14,000, but that's the typical quoted range. Above that is ultrasound. Other animals, it's different. So you've got ultrasound, you can see that's higher. The acoustic range is 20, 20,000. Infrasound, we don't really talk about, but that's below. So between 1 and 20 hertz. So some very low frequency sounds are present on the planet as well, like earthquakes. Oscilloscope sound, we've got to understand how these screens work. So what do the squares up mean? So we're looking at amplitude and down amplitude as well from the middle. And we want to know how to work out what these little squares mean. So we're looking at divisions per second and volts, divisions for volts of the screen. So it's basically a way of seeing what's happening on the oscilloscope screen to show different sound waves. And so relating to that, we need to look at pitch and loudness. So pitch relates to the frequency of vibration of the source, lower pitch, higher pitch, so more sound waves in a given time. And the amplitude, we said, was the height. So it's either louder or quieter. You specifically need to know the concept of a longitudinal wave. So we talked before about longitudinal waves. It means that the particles move in a direction parallel to the progression of the wave. They carry energy from one place to another, and they have an amplitude and wavelength. And sound needs a medium to travel through and cannot travel through a vacuum. So we've got here a direction of particle motion, backwards and forwards. You've got wavelength between compression and compression. And so you should be able to draw and label diagrams like that. We've also got experiments such as this. So there's two different experiments. You can hit a hammer on a bench, and a microphone will pick up a start time, a trigger for a timer. And then the sound wave propagates through the solid, and then it will trigger another stop idea, a little pulse on a microphone, and it will start and stop a timer. This one, 3.1 milliseconds. So I can actually work out the speed of sound with a hammer practical. We've also got another one, so I could have a signal generator and two microphones and a speaker. So I put apart and I pick up two waveforms. And what I do is I get it so that they all match up, and then I move the microphone a whole wavelength away, and the one wave at the bottom or the top, depending on how you've configured it, the wave will move across. You'll watch it move across. That distance then will effectively be the wavelength of the wave, and you can again work out the speed of sound. So you should be able to explain both practicals. There is another one where you could always make an echo on a wall, or you could clap two blocks together, let it go about 100 meters and then stop the timer. That's another way to work out the speed of sound, but you've got to be able to talk practically about different methods. There you go, that's sound waves in IGCSE physics.